Greetings and welcome to the 22nd and final clinic of linear algebra for this semester. We're going to be focusing on problems dealing with diagonalizing a square matrix. All right, so the idea behind diagonalizing a matrix is first we want to find all of the eigenspaces, right, and a basis for each one. So we're going to start the same way we did with our last clinic. So we want this determinant. And that winds up being lambda squared minus 5 lambda plus 4 to 0. Okay. So we get as our eigen values 1 and 4. Right, now, of course, this now automatically guarantees that we can diagonalize this matrix. Right? It's a 2 by 2 matrix. We have 2 eigenvalues. So let's go ahead and find eigenspace for the eigenvalue lambda equal to 1. This will reduce. This means that x1 is negative 2x2. So we have as our eigenspace, right, the set of all vectors of the form negative 2r, such that r is any real number. Which means that a basis would be negative 2, 1. Do the same thing now for lambda 2 equal to 4. Right, that'll reduce this. Right, this means that x1 is equal to x2, right? And so we get as our eigenspace the set of all vectors of the form R, such that R is any real number. So a basis, right, would be 1, 1. Therefore, to diagonalize this matrix, P is equal to this here, right? So I took the basis element of the first eigenvalue, made that the first column. See that? Basis element of the second basis, made that the second column. So that is our P. Our D would then be the matrix 1, 0 and 0, 4, right? It's just the diagonal matrix where the elements on the diagonal are the eigenvalues. Now you want to be careful. Since I made the first column the basis of the first eigenspace, that means that the first column of D will have to be the eigenvalue that is associated with that eigenspace, in this case, 1. Right, so you could have just as easily said that P, right, is 1, 1, negative 2, 1, and then D would be 4, 0, and then 0, 1. let's now look at this 2 by 2. Of course, this means that we'd be able to write our matrix as, so remember, and I believe it's that form. No, I mixed that up. It is P, D, P inverse. Okay, so we want to do now the same process for this. This will give us the characteristic polynomial lambda squared minus lambda minus 2, set that equal to 0. And we find that lambda is either -1 or 2. Again, 2 eigenvalues for 2 by 2. We can definitely diagonalize this matrix. That is guaranteed. And so let's start with lambda being -1. Oops. We'll reduce this. Okay. Obviously, then x1 has to be -x2. And so the eigenspace associated with this eigenvalue, set of vectors -r, such that r is any real number. And that means a basis would be the set of the vector -1, 1. All right, so now for the second eigenvalue, which is 2. Right, that'll RREF. We'll reduce to this. Right, this means that x1 is -4x2. So the eigenspace is the set of all vectors of the form -4RR, such that R is any real number. And that means a basis is the set of the vector -4, 1. To diagonalize this matrix, then, we just say that P, right, is the matrix -1, 1, -4, 1, and D is the matrix -1, 0, 0, 2. All right, let's look at a 3 by 3. So if we take a look at this, there's that determinant. set it equal to 0, we clearly get lambda is either 2 or 4. I'm sorry, I really messed that up. Ignore that, this is not a diagonal matrix. We're going to get lambda minus 4 times lambda squared minus 4 lambda plus 3. Set that equal to 0, and we get that lambda is 1, 3, or 4. 3 eigenvalues for a 3 by 3 matrix. That means that we can diagonalize this matrix. It is guaranteed. Let's go ahead and find the eigenspaces, starting with eigenvalue of 1. We'll reduce this and we get so we have that x1 has to be negative 2x3 and x2 has to be negative 3x3. Eigenspace. The set of vectors of the form negative 2r, negative 3r, and r. Right. Such that r is any real number. So for a basis, we can take the set 2, 3, negative 1. Notice here I let r be negative 1 instead of positive 1. It doesn't matter. You can let r be positive 1, right? And then you'd have negative 2, negative 3, 1. Looking at the eigenvalue 3, this will reduce. So x1 is 2x3, x2 is negative x3. Oops. So lambda 2, right, our second eigenspace, be a set of vectors of the form 2r, negative r, r, such that r is any real number. That means a basis for this eigenspace is the set 2, negative 1, 1. And finally, the third eigenvalue, which is 4. And that will reduce. This means that x1 has to be x3 and then x2 has to be 0. Eigenspace. Then be set of vectors of the form r, 0, r, where r can be any real number. This means that a basis is the set of the vector 1, 0, 1 So our P matrix. First column would be the first basis. Second column, the second basis. Okay, and then third column, the third basis. And their D matrix. 1, 0, 0, 0, 3, 0, 0, 0, 4. Let's take a look at another 3x3. So we take a determinant. We get lambda minus 2 times lambda squared minus 4, set that equal to 0. And we find that lambda is either 2 or 4. So here we have two eigenvalues for a 3x3 matrix. This does not mean that it is undiagonalizable right away. What we have to do is check, right? So we have to have total dimension of 3. In other words, we have to be able to find 3 linearly independent eigenvectors. Let's start with I am very sorry. It should be -2 and +2, right? Not 2 and 4. So let's start with -2. This will reduce. Means x1 is -x3, x2 is 0. And so the first eigenspace, set of vectors of the form -r0r, such that r is any real number, meaning we have, as a basis, we can have set of the vector -1, 0, 1. So now for 2. In order for us to be able to diagonalize this matrix, we better be able to get 2 linearly independent eigenvectors out of this, meaning the dimension of this eigenspace had better be 2. This will reduce. And we can see already that this is not going to give us an eigenspace of dimension 2. We get that x1 is a third x3, x2 is 0. Eigenspace, set of vectors of the form r over 3, 0, r, such that r is any real number. So we take for basis the set 1, 0, 3. Therefore, we conclude that this matrix is undiagonalizable. Okay, so let's take a look at this 3 by 3. Take that determinant, what we get is lambda minus 3 times lambda squared minus 4 lambda plus 3. Set that equal to 0, we get eigenvalues 1 and 3. Once again, 2 eigenvalues for 3 by 3. So we better get one of the eigenspaces to be dimension 2. Let's start with the eigenvalue 1. We'll reduce this. X1 is 0. X2 is negative X3. So the eigenspace set of all vectors of the form 0, negative R, R, right, such that R is any real number. So we take as our basis set 0, negative 1, 1. Let's now look at the eigenvalue 3. This row reduces. Meaning X1 can be any real number. And then X2 would have to be X3. So our eigenspace is a set of vectors of the form S, R, R, such that R and S, any real numbers. We take for our basis then set 0, 1, 1 and 1, 0, 0. Sum of the dimensions is 3. That means this can be diagonalized. So we take the first column to be the first basis element. Second column and third column, right? So the second and third columns will be the 2 basis elements for the second eigenspace. And then our D would be right, since the eigenvalue, the eigenspace associated with the eigenvalue 3 was dimension 2, right? We put 3 in the D matrix twice. And finally, let's look at a 4x4 matrix. We get as our determinant lambda times lambda minus 5 times lambda squared plus lambda minus 6. Set that equal to 0. And we get lambda is -3, 0, 2, or 5. Diagonalization is guaranteed. Right? We have 4 eigenvalues for a 4x4 matrix. Now we just have to determine the eigenvectors. Right, so start with the eigenvalue -3. This will reduce. So x1 has to be -x3, x2 has to be 3x3, and then x4 is 0. So the eigenspace is the set of vectors -r, 3r, r0, such that r is any real number. And we take as our basis then the set of the vector -1, 3, 1, 0. For lambda2 equal to 0, so the eigenspace or the eigenvalue 0, this will reduce. Meaning x1 is -x3, x2 is 0, and so is x4. So, eigenspace, set of vectors of the form -r, 0, r, 0. And we take as our basis the set of the vector -1, 0, 1, 0. Now for the eigenvalue 2. This will reduce. This is an 11. All right, that means that x1 is -11x3, x2 is -2x3, x4 is 0. Eigenspace, set of vectors, -11r, -2r, r0. And so we can take for our basis the set of the vector 11, 2, -1, 0. And finally, the eigenvalue 5. This will row reduce. Which means that x1, x2, and x3 are all 0, and x4 is any real number. So our fourth and final eigenspace is the set of vectors 0, 0, 0, r. And so we take as our basis set of the vectors 0, 0, 0, 1. All right, therefore, our P matrix first column is the first basis, second column is the second basis, third column is the third basis, and the fourth column is the fourth basis. And our D matrix is right there. And with that, the final clinic has come to an end. I hope you enjoyed this clinic series in linear algebra. As always, I thank you for attending, and I thank you so much for watching. I will see you when I see you.